Hello, welcome back to the channel. So we shall continue with molecular point groups. So in this video, I'll be taking all tetrahedral point groups. So under the heading tetrahedral point groups, in fact, we can have three different kinds of point groups, namely T and TH, then TD. Now we shall see all these three point groups and different operations possible on these point groups and examples for these groups in this video. So everywhere I consider 3D animations for better understanding. In our previous videos, we have discussed all these point groups. Say we had started with the molecules with low symmetry. There three different point groups were possible. Those were discussed. Then we had entered to molecules with high symmetry. So there are 7 different kinds of point groups. They were discussed. Then we had even come to this molecules with special symmetry, and under this heading molecules with special symmetry, in my last video I have discussed even linear point groups like C infinity V and D infinity H. Now let's continue with this molecules with the special symmetry itself. So next what we can have is, so if I broadly classify different point groups in this molecules with special symmetry, I can make it into 4 different categories. Say linear point groups, which is already covered. Then I can go with the tetrahedral point groups, octahedral point groups, and even icosahedral point groups, right? So though few of them, they are not very common, we shall just see what exactly exactly are these point groups and what different operations are possible under these headings. Now in this video I'll be taking this tetrahedral point groups under that T, TH and TD. So first let's start with T. So I have just continued the numbering. C infinity V it was 1 and D infinity H it was 2. Now this is 3. T, this is again it can be just it comes under the tetrahedral point groups itself. So order of this group, it will be H is equal to 12 different operations are possible, and here we don't have possibility like T2 T3 and all. It's just only one point group T, and again this is pure rotational point group, so only rotation operations are possible. Of course E is possible, and 4 C3s, C3 axis, 4 different C3 axis will be possible, and we know on each C3 axis we can consider 2 genuine rotation operations. So therefore on 4 such C3 axis, in total 8 operations are possible. Then 3 C2s are possible, and on each C2 1 operation is possible, so total of 3. So it comes to totally 8 plus 3 plus 1, 12 different operations are possible. And examples, very less examples are available for this point group. This is very rare point group. And C60F36, this is one such example. And the other example, calcium THF complex. So it's octahedral complex, but it comes to this point group T. So we shall see animations for these two. It's difficult to draw these structures definitely. So therefore directly we shall see this in animations. So this is the molecule C60F36. So one C3 axis that has been identified. Definitely this molecule, it will be very difficult to imagine to all possible symmetry operations in this case, but this is in fact T point group. So first one C3 it has been identified. I can just show the operation on this C3. So this is a C3 axis. So rotation by 120 degree, it brings back the molecule to the equivalent orientation. Then in fact 4 such C3s are present for this. So you can see 4 such C3s are present. Then along with that, even C2s are present. 3 C2s are present, as you can see here. So therefore C2 operations are possible, and even C3 operations are possible, and this is the point group T. This is calcium tetrahydrofuran complex. See this tetrahydrofuran, it's not a planar molecule. So therefore, though this is octahedral complex, this molecule it will not go to octahedral or any other higher point groups. So this settles to be T point group itself. So what we can see is C3 axis. So C3 axis, of course, it can be easily identified as we do in the case of octahedral complex. So if we just consider these 3 atoms, and if we make a triangle, center of this triangle, that makes a C3. So that we can see. So all these are C3s. Okay, so now what we can do is easily this C3 can be understood. Now if I rotate the molecule on this C3, so it brings the molecule to equivalent orientation. So therefore definitely it is C3. So along with this C3, as we can see here, 3 more C3s are present. So in total 4 such C3s are present. Now, along with these C3s, in fact, this is this kind of special C3s that they take the molecule to special point groups like tetrahedral, octahedral, and all. Now, even C2 rotations are possible. As it is mentioned, this T, it is purely rotational point group. So now even C2 axis, 3 C2 axes are present, and in this case, it's not that difficult to identify. So if we consider octahedral geometry to the molecule, so each opposite coordination sites, if we develop them as axis, those will serve as C2 axis. Maybe on one such C2 axis, I can just show the operations. So let's say on this C2 I rotate the molecule, and by rotation of 180 degree the molecule, it will come back to its equivalent orientation. Therefore it's C2. 3 such C2s are present, and therefore this is again pure rotational group T. The next point group that comes under this tetrahedral category is TH point group. See, this H itself, it indicates that this is T. So T means certain operations like C3s and C2s, 4 C3s and 3 C2s, they were possible. So here also that is there, 4 C3s and 3 C2s, that is there. Maybe we can say that is the essential requirement to call a point group to be T. And now along with that H, if it is included, that means that horizontal planes are there. And now here it is not just one horizontal plane, 3 horizontal planes. They cannot be distinguished. All those they should be called as horizontal planes itself. So 3 horizontal planes, they will come along with these proper rotations. And along with this, some other operations, they will be implied. So we know that if we have a proper axis, then sigma h, definitely there will be possibility, there can be the possibility of s axis, improper axis. So that is there here. T3 axis along with that S6 axis is also present, and one of the operations on this S6 that can be even taken as I. So it's S6 3, that operation, it will be taken to be I. So now totally H order of this, that point group, that is total number of operations possible on this point group, it will be 24 E, and on 4 C3s, each C3 it is 2 operations, so it's total of 8, and 3 C2s, on each C2 1 operation, so it's 3 sigma H, 3 operations, 4 S6 on each S6 except this I. When we leave this I, so we can say that on each S6 we can have 2 operations, therefore 8, and inversion center, if it is considered separately, it will be 1. So if we just take a sum of this, it will come to 24. So this we can say some known molecules or some molecules which we commonly encounter, they can exist in this TH point group. Though they are rare, usually under this tetrahedral point group, only one point group TD it will be discussed, but under tetrahedral we can have T, TH and TD. So TH, of course, some examples are available. This is pyridine iron complex, iron pyridine complex. This we shall see in animation. There we exactly understand the structure of this. So this belongs to this point group TH, and hexa nitritothorium. So this also, it comes to this, acts as bidentate ligand. Coordination number of this, it will be 12. So this also, when we see the structure, it will be clear to you. It will be clear to us. And these 2 molecules, they come to this TH point group. This is iron pyridine octahedral complex. So pyridine, it is planar molecule. It's occupying all 6 coordination sites of iron. So now in this case, C3 axis, it can be understood very easily. It's not difficult because it's octahedral complex. And if we consider this equilateral triangle, or one face of octahedron, and center of that, it will serve as C3 axis. So one such C3 axis, let me just try to identify. So this is the C3 axis, and on this I can rotate the molecule exactly by 180 degrees so that I'll get equivalent orientation. So that's how this is C3 axis. And in fact, we know for octahedral complex we can identify 4 such C3 axes. So 4 such C3 axes can be easily identified. We can see them here. So 4 such C3 axes are present. So now along with this, if we want to call the molecule in T point group, it is 4 C3 axis, along with that C2 axis must be present. See, even C2 axis, they are there here, and easily it can be understood. So 2 coordination sites, opposite coordination sites, 2 transpositions, if they are developed as axis, that will make that will give a C2 axis for this molecule. This can be easily understood. So therefore this molecule, even it has C2. Now, how many such C2s are present? In total, we can find definitely 3 C2s. So 4 C3s plus 3 C2. This takes the molecule to T. And now it is said to be TH. It's not just T point group, it's said to be TH. It's because it has horizontal planes. not just one horizontal plane, 3 horizontal planes it can be easily identified. So therefore all these 3 horizontal planes, they are identical, therefore this molecule it goes to TH. So along with this, even S6 axis is present, and on each S6 axis 2 different operations, S6-1 and S6-5 operations are possible, and this S6 axis it is definitely collinear with C3 axis. So as we can see here, if we make again a triangle, and if we take the center of the triangle, on that if we can develop an axis, that will be in fact C3 axis. That C3 axis it is S6 axis too. So it's because if it is S6 axis, it should be C6 rotation. Along with that, sigma is to be performed. So C6 means rotation by 60 degree. So this nitrogen, or say this, if we keep as reference point, so this will come somewhere say above this atom, right? So these 3, let's say they are in one plane, and remaining 3 they are in one plane by 60 degree rotation, that is C6 on rotation by C6 axis on C6 axis rotation. So this comes exactly above, right? But that is not identical orientation. But if we take a reflection, then this atom which is present above, that will go back, and that results in equivalent orientation that we can see here. So that's how S6 molecule exists. So it is taking anti-clockwise rotation by 60 degree. Carefully we need to observe the things, and then after that it goes to, so now it has performed just S6, then now it is followed by C6 followed by sigma. So that is S6. S6 do exist for this. Of course, in S6, one of the operation S6-3, it will be nothing but inversion operation. So therefore inversion center, that's also present here. It lies at the center of the metal atom, and this can be easily understood, not that difficult. So all atoms, they get inverted, right? So that's how now this point group, it has 4 C3 axis and 3 C2 axis along with that H, and it should be taken to sigma H, TH point group, not sigma H, TH point group. So this is thorium nitrate complex. Nitrate, it will serve as bidentate ligand in this case. So we can say that if it was a typical octahedral complex, just maybe this point we could have considered it as a coordination point. Now it is, because it is bidentate ligand and 6 such ligands are present, say it will be coordinated in this way. So now in this case also same, 4 C3s we can easily identify. So 1 C3, let me show. This is 1 C3, and on this the molecule, it can be rotated by an angle of 120 degree to get identical orientation, and we know that for a T it should be 4 such C3s, and definitely 4 such C3s are present for this molecule. And then along with this, C2 should be present, and 3 C2s are definitely present for this one such C2, right? So as I said, say if we consider these points to be coordination sets, definitely then we can call this as octahedral complex. And considering these nitrogen atoms, it is easy to identify C2 axis. This should be C2 axis, not difficult to imagine if you know the structure of molecule. So it is C2, and in total 3 such C2s are present. So 4 C3s plus 3 C2s, now it makes, or it takes the molecule to the T category. And now sigma H, along with this sigma H, they are also present, and not 1, 3 such sigma H will be present. So all 3 sigma H, these are sigma H. So therefore this molecule definitely should go to TH point group. Now inversion center, it will be present, and let me just demonstrate S6 axis. As it was mentioned earlier, the C3 axis, it is even collinear with S6 axis. So on this axis, rotation by 60 degree followed by plane reflection operation on a plane which is perpendicular to this axis, that brings the molecule to original orientation. We can see that. So to understand the operations, we can just keep the position of nitrogen atoms as a reference, so that we can easily understand all different operations. So now this is S6 operation, and that is the molecule THNO3 6 times 2 minus. In fact, even same molecule, probably cerium complex, it can form similar complex, that should also come to this point group itself. The next point group, it is tetrahedral point group. This is most common under tetrahedral point groups. TD, it is most common. Here also order of the point group, it will be 24 itself, but definitely this is different than TH. So in case of TH, we had horizontal planes. So here what we will be having is 6 dihedral planes will be having, and because these planes are dihedral, this point group, it is called as TD point group. So number of operations here it has been mentioned. So this is essential requirement for T, that is 4 C3 axis and 3 C2. They are there here. Sigma H, they are not present, but sigma D's are present. So 6 such sigma D's, and this we know on 4 C3s 8 operations, and on 3 C2s 3 more operations. And along with this, here in this case, S4 axis it do exist, and same S4 on S4 axis. On each S4 axis, 2 genuine improper rotations will be possible, which can be called as S41 and S43. And therefore on 3 such axes, a total of 6 operations will be possible, and in total 24 operations will be possible in case of this tetrahedral TD point group, tetrahedral TD. So the most common example, best example for this is methane, which is a tetrahedral molecule and which goes to tetrahedral TD point group. And a regular tetrahedron solid geometry, if we consider, that can also be said to be this TD point group. And neopentane, so carbon atom, it is substituted with 4 methyl groups, so that can be called as neopentane. So there also we can say that the point group, it will be this TD itself. So here for CH4 being common, we shall just see in 2D also, we shall try to understand at least axis, all different axis and also different symmetry elements. So first thing, it has C3. So C3, each CH bond, it will act as C3. And if we keep this molecule methane in this inside this a tetrahedron, then it will be easy for us to identify symmetry elements in this. So now see this C3 axis, it is passing through 2 opposite corners, and along with that even one CH bond it is coming. And for a cube like this, we can have totally 8 corners. So if we have 8 corners, to make one C3 axis, what we require is 2 corners. So now each set of opposite corners, they make C3 axis, or in other words, in simple words, each CH bond, 4 CH bonds we have, each CH bond that makes C3 axis. So this is C3 axis for this. Now to understand C2 axis, all these things, all these operations, we shall see it in 3D animation, but it's good to understand. It can be understood in this 2D diagram also. So this axis, so if we take this to be cube, and let's say it's this axis, it is bisecting this tetrahedral angle HCH angle. So that will serve as C2. On this, if molecule is rotated by 180 degree, this hydrogen it takes this position, this hydrogen it takes this position. Simultaneously, even these 2 hydrogens, they change their position. Therefore, this axis, it is C2 axis. And we can easily understand 3 such C2s will be possible. One, it will be this, the other one, it will be like this, and the third one, it will be like this, right? Fine. 3 such C2s will be possible, and these C2s, they are collinear with S4. So S4 also, it can be understood very easily. See S4, just if I illustrate one operation here. So by S4 means it is C4 rotation by sigma. So just this hydrogen by 90 degree rotation, it comes here, and this hydrogen, it comes here. But when we take opposite sigma, this hydrogen which was present here, that will reflect back here. Similarly, this hydrogen will reflect back here. That's how this is S4 axis 2, and S4 operations are possible. And the planes, 6 sigma D planes, they have been illustrated while taking symmetry element planes itself, dihedral planes itself. Simple way to understand all 6 sigma D planes in this case, any 2 opposite edges like this, if they are joined, so that makes a plane. So on this plane now, 2 CH bonds will come. So this is one CH bond which is there in this plane, and this is one more CH bond which is there in this plane. And other 2, this plane, it will be exactly bisecting the other 2. Therefore, this will act as sigma D, and this plane, it passes in between 2 C2 axes. So here just one C2 axis I have indicated here. So this plane itself, if I consider, so this is also one more C2 here. So this plane, it is passing in between 2 C2s. Therefore, this plane, it is sigma D. And to understand 6 sigma D's, it is very simple. So to make one sigma D, what we require is 2 edges, and for a cube 12 edges we will be having. So therefore 12 edges in total, it should give us 6 sigma D's. So that is the point group tetrahedron. Now we shall see maybe for methane molecule all these operations in 3D animations we shall see. This is the molecule methane. So in this case also it is a tetrahedral point group itself, so which means that it has 4 C3s, and 4 C3s in this case it's not that difficult to imagine. Each CH bond, it can serve as one C3 axis. So as we can see here, all CH bonds have been made as one C3 axis. So this is one C3 axis, this is one more C3 axis, this is one more C3 axis, this is fourth C3 axis. So on any of this we can easily imagine this operation. In fact, we can rotate the molecule by 120 degree. It results in identical orientation. So that's how it has 4 C3s. So 4 C3 axes are present. So along with that 4 C3, it has even C2s. So these C2s, how they are exactly, they are bisecting this angle. So if we take a HCH tetrahedral bond angle, that will be bisected by C2s. So one of such C2s has been shown here. So this C2, we can easily say that is bisecting this angle, and on this C2 the molecule, it can be rotated by 180 degree to get identical orientation. Therefore it's a C2 operation, and C2 axis is present. And now it's not one such C2 axis, but 3 such C2 axes are present. So as it has been described in a cube, this molecule, it can be kept in cube, and all the symmetry elements, they can be understood very easily. So there we have understood that 3 such C2s are possible, and we have definitely 3 C2s. So along with that, even sigma Ds, so 6 different sigma Ds are present. One such sigma D, if at all I have to show, so I should just consider 2 hydrogens, and the plane which bisects these 2 hydrogens, that will be a reflection plane, because if I perform the operation as I can do that here, so this atom, it takes this position, this atom, it takes this position, therefore it's a reflection operation. And it's not just one such sigma D for this. So in total we have 6 such sigma D. So altogether I have identified, and this has been discussed earlier too. So 6 sigma Ds are present, and that's how now see what all we have for this molecule is 4 C3s we have, along with that 3 C2s we have, and plus sigma Ds. Therefore this should be TD point group. Now along with this S4, it will be generated automatically. So S4, it is collinear with C2 axis. S4, it is collinear with C2 axis. Maybe one such S4 axis I identify. So let's say this I am identifying. So now you can understand that S4, it means C4 followed by sigma. So C4, it refers to rotation by 90 degree. So if these two, they are in the above plane, and these two, they are in the below plane, if I rotate the molecule by say 90 degree, then this, it takes this position, this, it takes this position, but it will be above the carbon atom. So therefore it will not be equivalent orientation. Further, when I take reflection in opposite plane, so these two which are present above, they tend to go back, and that will result in equivalent orientation. That's how S4 axis, it is present for this molecule. You can see that. So now 90 degree rotation. So here it stops, here rotation stops. Now from this point it is reflection. Therefore even S4 axis is present, and therefore this point group, it is tetrahedral point group, methane molecule. And definitely if we consider regular tetrahedron, for that also similar set of operations it will be possible. So hope this video, it has given you a clear idea of all different kinds of tetrahedral point groups. So if you have liked this video, you can give a like, and share this video to your friends. And if you are not subscribed to channel, please do subscribe to this channel. Press bell icon for new video notifications.